Green hydrogen is often discussed as if all electrolyzers behave the same way under renewable power. They do not. This single misunderstanding sits at the center of many underperforming hydrogen projects. The issue is not whether electrolyzers can ramp. The issue is how different electrolyzer technologies age when exposed to intermittent power. PEM and alkaline electrolyzers respond to variability in fundamentally different ways, governed by different physics, different materials, and different failure modes. Treating them as interchangeable assets under fluctuating renewable supply is not an engineering shortcut. It is a category error. At first glance, PEM appears superior for renewable integration. It ramps quickly, responds instantly, and handles dynamic loads far better than alkaline. This has led to a widespread assumption that PEM is inherently suited for intermittent operation, while alkaline requires baseload conditions. That assumption is only half true, and the missing half is where projects quietly bleed capital. PEM tolerates variability better in the short term. It does not tolerate unmanaged cycling over time. Alkaline struggles with rapid ramping, but when protected from it, it ages more predictably. These distinctions matter because electrolyzer degradation is not linear, and it is not symmetric across technologies. The most important clarification is this: ramping capability and lifetime durability are not the same thing. PEM electrolyzers are excellent at changing output quickly. That does not mean they can endure frequent start-stop operation without consequence. In fact, PEM systems often experience more severe irreversible degradation under cycling than alkaline systems, even though alkaline cannot ramp as quickly. This paradox sits at the heart of modern hydrogen project design. Inside a PEM electrolyzer, electrochemical reactions occur across a thin polymer membrane coated with precious metal catalysts, primarily iridium on the anode and platinum on the cathode. These materials enable fast response and high current density, but they are sensitive to transient operating conditions. During startup and shutdown events, voltage spikes occur. Local potentials exceed steady-state levels. Catalyst oxidation and reduction cycles accelerate dissolution. Iridium migrates into the membrane and is permanently lost. This is not recoverable degradation. Once catalyst loading is reduced, performance declines irreversibly. Membrane hydration adds another layer of vulnerability. PEM membranes must remain hydrated to maintain ionic conductivity. When power drops or shuts down, water transport changes. Membranes dry unevenly. Upon restart, rehydration is non-uniform, creating localized hotspots and mechanical stress. Repeating this cycle dozens or hundreds of times per month compounds damage exponentially. 1 hour of cycling damage is not equivalent to 1 hour of steady operation. It can equal tens of hours of usable life consumed in a single transient. Thermal effects amplify this problem. PEM stacks operate at relatively low temperatures compared to solid oxide systems, but rapid power swings still introduce temperature gradients across tightly packed layers. Different materials expand and contract at different rates. Seals fatigue, interfaces weaken. Over time, mechanical degradation accumulates in ways that are invisible in short-term performance data, but devastating over asset life. This is why PEM electrolyzer degradation under intermittent power is driven less by total operating hours and more by cycling frequency. A PEM stack that runs smoothly at variable load but avoids shutdowns may last years longer than one that is frequently turned on and off, even if total hydrogen output is identical. This distinction rarely appears in high-level project models. Alkaline electrolyzers fail differently. Their chemistry relies on liquid electrolyte and porous electrodes rather than polymer membranes. They are slower to ramp and more tolerant of steady operation. Under baseload conditions, alkaline stacks degrade slowly and predictably, often around 1% per year or less. However, alkaline systems are vulnerable to rapid load changes. Fast ramps can cause gas crossover, electrode stress, and efficiency loss. For this reason, alkaline electrolyzers are often operated conservatively when connected to renewables, either through curtailment, buffering, or grid support. The critical difference is that alkaline degradation under stress is often operationally avoidable. Slow the ramps, stabilize the load, and alkaline systems behave well. PEM degradation under frequent cycling is electrochemically intrinsic. Even when ramp rates are controlled, repeated shutdowns impose irreversible damage. This makes PEM more sensitive to how intermittency is managed, not less. OEM behavior reflects this reality, even when marketing language does not. ITM Power has focused heavily on refining PEM stack architecture, reducing iridium loading, and developing control strategies that limit harmful operating transients. These efforts are not about efficiency alone. They are about preserving stack life under real-world conditions. Warranty language increasingly reflects acceptable cycling limits and defined operating envelopes, shifting risk back to project developers if those envelopes are exceeded. Nel ASA operates across both PEM and alkaline technologies, and its system-level messaging has grown more explicit over time. The company emphasizes integration, power quality, and operating discipline rather than raw stack metrics. This is not accidental. When a supplier offers both technologies, it becomes impossible to ignore that their degradation behaviors diverge under intermittent power. Sunfire, particularly in solid oxide systems, makes the contrast even sharper. Solid oxide electrolyzers require stable, high-temperature operation and are fundamentally incompatible with renewable intermittency without substantial buffering. Sunfire's designs integrate heat and steady industrial power, not volatile grids. The technology excels precisely because its operating regime is respected. The lesson applies equally to PEM and alkaline systems. The problem arises when project developers treat electrolyzers as flexible appliances rather than electrochemical assets. Many financial models assume that if an electrolyzer can ramp, it can cycle freely. They assume degradation scales linearly with hours. They assume replacement schedules are predictable. These assumptions fail most dramatically for PEM systems tied directly to volatile renewable output. In practice, PEM projects often compensate by adding complexity. Batteries smooth input power. Grid connections provide baseload stability. Control software limits shutdowns. Stacks are kept warm even when idle. Each mitigation improves durability but adds cost. Hydrogen becomes more reliable but less cheap. This trade-off is rarely acknowledged up front. Alkaline projects make different compromises. They accept slower response and lower theoretical utilization in exchange for longevity. They often operate closer to baseload, even when connected to renewables. Curtailment is tolerated. Hydrogen output is smoother. Over time, total cost of ownership can be lower, even if headline flexibility is reduced. Again, this is not a technological failure. It is an optimization choice driven by physics. Geography amplifies these effects. Regions with volatile solar ramps, turbulent wind profiles, or weak grids impose harsher cycling regimes. PEM stacks in these environments age faster and less protected. Alkaline systems may struggle operationally but survive longer if stabilized. Identical electrolyzers deployed in different regions can experience radically different lifetimes, yet many global hydrogen cost models ignore this entirely. This divergence between modeled and actual degradation explains why some hydrogen projects underperform financially without suffering obvious technical failures. Stacks operate, hydrogen flows, but replacement CAPEX arrives earlier than expected. Maintenance costs rise, availability drops subtly, debt service margins tighten. By the time issues surface, contracts are signed and assumptions are locked. Warranty structures reflect this growing awareness. OEMs increasingly specify ramp rates, cycling limits, minimum loads, and acceptable shutdown frequency. Exceed them, and coverage erodes. This shifts operational risk to developers and operators who may not have fully internalized the implications during early modeling. The industry response has been pragmatic rather than dramatic. Engineers are adapting designs quietly, controls are improving, hybrid architectures are becoming standard. The public narrative still emphasizes scale and cost reduction, but beneath that narrative is a recognition that electrolyzers must be treated as sensitive industrial assets, not shock absorbers for renewable volatility. This distinction between PEM and alkaline degradation under intermittent power is not academic. It determines which projects survive stress and which quietly degrade. It explains why some high-profile deployments struggle while less ambitious systems endure. It clarifies why hydrogen economics remain stubbornly resistant to simplification. The takeaway is not that PEM is bad or alkaline is superior. The takeaway is that technology choice must match operating regime. PEM excels when variability is controlled, not ignored. Alkaline excels when stability is prioritized, not sacrificed. Solid oxide excels when intermittency is removed entirely. Each technology works when its physics are respected. Green hydrogen will not fail because electrolyzers cannot ramp. It will fail when projects assume ramping equals durability. The next phase of hydrogen deployment will be decided not by efficiency curves, but by how well developers internalize degradation physics and design systems accordingly. The projects that survive will not be the ones with the most aggressive utilization assumptions. They will be the ones that understand how PEM and alkaline systems age differently under stress and engineer around those realities. That is not conservatism, it is competence. If you want to understand how real hydrogen projects manage these distinctions, how OEM warranties translate into financial risk, and how system-level design determines long-term survivability, that is exactly what we unpack inside H2 Hub by Renewable Energy. This is not a theory platform. It is an execution platform built around what actually breaks, what quietly degrades, and what survives system stress. Hydrogen's future will belong to projects that respect electrochemistry as much as ambition.